All right, huge crowd today. Everybody, alternate seats. If you guys are welcome to sit way in the back if you want, but you can also move down. It'll be cozier, whatever you like. All right, so today what we're going to talk about is how you search through documents that are not structured in the way that we say search on the web, or how do search boxes work in general. And we'll take this in two doses. We'll see how much we get through today. Maybe we'll get through all of it. Maybe we'll get through the first half or the first half in a bit. You know already from your studies in this class most of what it takes to build an elementary Boolean text search engine. And so that's what we'll spend the first half of the lecture doing. And really it's going to just be putting together concepts that you already know. At some level, it's a schema design and data wrangling problem. So it's a little bit of what you did in homework 1 of converting documents into data, a little bit of the schema design of what's the schema you want that data to be in, and then the rest of it just kind of flows from what you know about relational operators. The second half of the content is the more modern material, which we're just going to go through briefly. I mean, both of these are really high level, but on ranking. So, it's nice to know that there's 100 million hits to your search on Google, but if they show them in random order, that would be a big problem. So ranking is sort of the second piece of the puzzle. Ranking got way better in the era of the web over the last, say, 15 years. And before that, it was pretty primitive. But what we'll do today, essentially, is kind of demystify these topics, give you a sense of how they work. I do not expect you to understand this in the depth that you understand some of the other material. You can take an entire class on search. There's lots of special case thinking that applies specifically to search. The goal today is to give you the sense that you've already got the building blocks in terms of the data management to go tackle these kinds of problems. Okay, a little history. Information retrieval is the name of the sort of field of study around document search. And it goes way back to the late 50s and was traditionally a completely different thing, or it's got a whole different heritage than databases, though both have their roots at IBM. So this goes back to 1959. This guy Hans Lun at IBM had a system called Keyword in Context. So think about the 1950s. It's a little hard, but computers are, I don't know my history even well enough. I think this may be pre-disk drives, pre-drums, I'm not sure. But you have a very small amount of memory and storage you're dealing with, in the order of kilobytes. And this guy is envisioning a world in which all sorts of paper documents like books and office documents have been turned into digital documents. And then he's asking, how could you search in them? It's a crazy hypothesis that this could ever exist in 1959. I mean, it's like, this guy is so far ahead of his time, he's crazy. And he comes up with the basic Boolean search approach that is at the core of what we do today on the web. So really pretty cool stuff. Very, very much before its time. Very sort of notional idea. Maybe this would be a thing you could do with computers. In the 60s and 70s, there was a guy named Gerald Salton at Cornell who did quite a bit of work in information retrieval when the field wasn't really very, it wasn't considered very important or interesting by most people. And he had a system called SMART that did not only the keyword search, but some of the early work on ranking. And this is around the same time that relational databases are happening. So this gives you a sense of history. The relational database is being invented, as is the sort of ranked information retrieval system. Obviously, there's been a ton of work since when I was coming up in the 80s and 90s in school. Information retrieval was pretty dormant. It was sort of not very interesting. There weren't any businesses making money at it. Nobody was really using it. You can sort of imagine that maybe the federal government had a lot of documents that they thought might be important to bother to turn into digital form and index. But most organizations, it really wasn't worth it. So companies that sold products for information retrieval at that time were trying to sell to, the story was sort of, there are documents like manuals in your corporation that would be really good for your employees to be able to go find things in, and so you should buy an information retrieval system. But before the web, there just wasn't that much interesting data in document form that was digital around. Why would you want to index the works of Shakespeare? Who really is going to search through that stuff? It just seemed a little bit like whatever. And they didn't work that well, to be quite honest, because there wasn't enough data and enough sort of interesting statistics in that data to really drive good search engines. And when the web happened, quickly became obviously really important. Some of the pioneering work on web search was done here at Berkeley by Professor Eric Brewer and his team, who built the first scale-out, shared nothing parallel web search engines in a research project and then company called Ink2Me, which subsequently was acquired by Yahoo. Predates Google. So that's a little bit of history. The products, in terms of what was in information retrieval and what was in databases, have long been separate engineering artifacts. So the information retrieval products were originally these document management systems that were used by libraries and government and law firms. And the exciting stuff really happened with web search and advertising. Right? There is still a market in enterprise search, but it's not a very big market. It's really all about the web. Okay, so here's how we're going to attack the topic. We'll look first at this naive Boolean search on keywords. So which documents have which words? Right? And the answer sets will not give you good rankings. We'll give you arbitrary rankings. Second, we'll look at ranking the results. And there's a bunch of stuff we're going to skip. There's a whole bunch of things. If you crack open an information retrieval textbook, you'll learn all about various ways you can compress your text and compress your indexes to make them go faster. And there's all kinds of bells and whistles, many of which are the kinds of engineering details that if you're going to really do it for dollars, you have to get it right. And many of them have to do with the human language, so tense and plurals and synonyms and related words. A lot of natural language processing, kind of nuts and bolts. So we're not going to go into any of that today. All right, from 1,000 feet, an information retrieval system and a database management system seem really, really different, and a lot of people don't consider them to be the same at all. To me, they're like basically two different skins on the same technology. I think they're very similar. So an information retrieval system, the query language has imprecise semantics. When you go to Google, you don't expect that you get the right answer. You expect that you get interesting answers. When you go to your accounts receivable database, you expect you get the right answer, right? So the database has precise semantics. The information retrieval system, it's imprecise. Obviously, the query languages are different. Information retrieval systems have this very easy-to-learn query language, which is just keyword search. And databases have a more complex language, SQL. And then a lot of people get all hung up on the idea that, information retrieval is on unstructured data, and databases are about structured data. And I hope I'll convince you today that structure is in the eye of the beholder. Everything has structure if you want to impose the structure on it. And in some sense, information retrieval systems are just as structured, if not more structured, arguably more structured than database management systems. All right, so data being structured is really a kind of ambiguous notion. So we'll talk about that. Information retrieval systems are read mostly. You don't tend to update things. Google doesn't have an update box. It only has a search box. You cannot submit transactions to Google. Unless you're buying stuff, right? And as a result, the documents are added in batch and only occasionally. In a traditional database system, you'd expect, at least for some applications, that there's quite a lot of updates and they're interactive. And then the information retrieval kind of semantics, typically very unusual in a like web search engine to return all the results to a query. But in a database system, that might be a common usage. Okay. Under the hood, though, really not as different as they might seem, but they're different enough that no one has built a single system that does both of these things well. Okay, so it's probably not worth trying to tune the algorithms that you've learned to put them together in a system that does both of these. You make some trade-offs along the way. There's an argument that the reason SQL databases are the way they are is they try to do a lot of different things. They do analytics queries, they do transactions. They don't have a sort of specific application that they're built for, their general purpose. An information retrieval system like Google's crawler and search engine are very special purpose. Right? They do it one thing, and they do it really, really well. And when you do that, you tend to invest in a lot of details that wouldn't work for other things, and that kind of takes you down a path of specificity, and you have to leave generality behind. But you get extreme performance scale, quality on the application domain you want. So text search is really a custom application of data management in some sense. Here's one way to look at kind of the architecture stack, and this is highly simplistic, but I just want to give you a sense of things. So on the left is the boxes that we tend to look at as a database management system. So queries come in the top. They're optimized. There's an execution layer with iterators. The relational operators implement those iterators. And then down at the bottom, we have custom files and access methods, buffer management, disk space management, all of which interact with concurrency and recovery, which we're going to learn about after break. All right, so that's kind of the database management system world. In the search engine world, you don't bother with all the storage stuff because you're not doing interactive updates anyway, and you don't have to worry about concurrency control. Recoveries happen handled with much coarser grain techniques, basically just by replicating stuff. Okay? So the operating system file system at some level takes care of all the storage in most search engines. Above that, there's usually one index. It's the access method. There's kind of only one for serving queries. And there's really only one query, as we're going to see. That's what I meant by this is more of a custom application. It's really got one query, and you optimize it yourself. You optimize it in the engineering of this thing. And that one query just has to go really fast. It's the handle keywords over the corpus query. All right? And we'll see what sort of that looks like. And then there's extra stuff above that a relational database doesn't have, like your ranking algorithm, or really the collection of things that lead to your ranking algorithm. And queries, when they come in, go through some string modification, and we'll talk about all these pieces. So a little bit different at the top, a little bit lighter on the bottom, and very highly customized in the middle. All right, so let's back out to sort of the model. This is going back to Hans P. Lund in the late 50s, okay? And this pervades. So the typical information retrieval data model is that, what is a document? You might think of a document as human language or as prose, but an information retrieval system thinks of your document as a big bag of words. Okay, just take all the words in the document. It doesn't matter what order they're in to start with. Let's just say it doesn't matter. And shake them all around. That's your document. All right, so that's not very structured. It's just a set. Actually, it's a multi-set, right? It's a bag of words. That's what a document is. And that's kind of where everything begins. All right, some details. All right. First of all, the first thing that you'll learn is that certain words are bad, and you don't want to index them, like the. Right? Or maybe HTML tags that aren't very meaningful, like decorative HTML tags like header. All right, so these are things where you could keep track of the fact that a document has the word the, but since almost every document has the word the, maybe you should just leave it out. Right? There'll be a lot of thes in your bag for every document. So those are called stop words, and they're things that you don't choose to pay attention to. The other detail, which is very much a English or at least Western language detail, is stemming, which is where you take language-specific rules to convert words to some sort of canonical form that leaves out things like tenses and plurals. Right? In English, we sort of have a good sense of how this works. Surfing and surfed all become surf. Right? Writing a good stemmer is a pain in the butt for English even, because English is a language with lots of special cases and lots of different linguistic roots. And I have no idea how you do stemming in a language like Chinese. I can imagine how you do it in some other languages I speak, but it's not like every language has suffixes for conjugation. So this has to be done in a language-by-language basis, which is gross. But there are open source libraries for this. It's sort of one of these things that's useful enough that people have done it by hook or by crook. Okay. So in the end, your document is a bag of stemmed words minus the stop words, right? Okay. So Boolean text search is the simplest form of search where you just want to find the documents that match any Boolean expression, ands, ors, and nots. So here's an example of a query. I want Windows and glass or door, and not Microsoft. I'm looking for, construction windows. And the query terms will be stemmed and stopped. So Windows will become window, okay, for example, so that a document that has the word window or windowed or windower, it will find all of those things. Query terms are stemmed stopped just like the documents are stemmed stopped. And so when your Google comes back and says 10 million documents found, it's pretty much at least an approximation of what you would get with Boolean search. Okay? So how do you implement Boolean search? It's actually pretty straightforward from what we've got in this class. So before we do that, though, let's a little terminology. When an information retrieval or a web search person talks about the index, when someone at Google talks about the index, they don't mean like there's a B tree over at Google. They mean something a little bit bigger than that. There is indexes like B trees inside of Google, but what they actually mean is there's really kind of both tables and indexes and a schema. So it's kind of a logical schema, which we'll go through in a minute, of how you represent the structure of the documents. Remember, documents are unstructured data, but they have an underlying structure, which we're going to capture pretty much relationally. And then there's going to be a physical schema over that logical schema, which is the actual B trees, what we would call indexes that you might build. And usually you don't store this in a database management system. You implement the B trees or whatever is your equivalent index for the system. You implement that by hand, and you store it in a file system yourself. We will use B plus trees in this discussion because we know them, but you can imagine them being replaced by something that is like, for example, an ISAM, something where you don't have to do interactive inserts. So something tuned more for the workload that we're having here, which is batch insertion, read mostly kinds of indexes with lots of compression to make the thing go as fast as possible. All right, but here's a simple version. It's a sort of an alternative 3 B plus tree kind of version. So the schema is like this. We're going to be given the terminology they use in information retrieval is a corpus, which means body in Latin. We will be given a corpus of text files. It could be the web, all right? It could be the works of Shakespeare. And we're going to turn that into a schema which has document ID. Every document needs to have an ID. Right, so we'll assign an ID to the document. And then the content of the document, which is the string that contains the document text. All right? From that files schema, we will create and populate another table called the inverted file. And this is kind of terminology that they like in information retrieval. The inverted file is a schema where instead of being keyed by document and giving you the content, it's keyed by terms in the document, and it gives you document IDs. All right, so you can look up in this thing a term like window, and it will give you doc IDs that go along with window. Now, I lied here in this slide, and it happened late at night, and I shouldn't have typed it. Term can't be a key of this relation, or that wouldn't work, because we'd only be able to get one document per word. So let me quickly fix this. Except it's so small with my contact lenses, I can barely see it. Wow. Hello. Good. Okay. So the inverted file is pairs of terms and doc IDs. So the word window can occur in many doc IDs. Okay. So what information retrieval people like to call this an inverted file or an inverted index. And this is what they mean by inverted. Instead of keying it on doc ID, we're going to do lookups by terms. All right. And I think in 1959, this was kind of a head scratcher. Like, wait a second. You're going to take a play by Shakespeare, and you're going to store it not as the play, but each word in the play you will store. And then following it, you will put the name of the play. Wow, that's really interesting. I would never have thought of that in 1959. Okay? But for us, it's just this is just a relational table. This is no big deal. But you do have to shred the document into terms and stem and stop them before you can populate this inverted file table. Okay? And then we'll build a B plus tree or a hash index or something like that on inverted file .term and do something like alternative 3 at the leaves. So if you look up Berkeley in this index, you get a list of all the doc IDs in sorted order, and this is going to be really important. Okay? Sorted order of doc IDs, all the docs that contain Berkeley. Okay? In information retrieval land, they call this thing at the leaf a postings list. Right? It will remain sorted. You got to keep your postings list sorted. All right? And with this data structure and that schema, you now can do single word queries. And you can look up Berkeley. That's how you find all the documents that contain Berkeley. Okay, so that's easy. And it's not really worth showing this, but here's an example of an inverted file taking text off of an old class web page, an old Microsoft.com homepage. You can look up databases, which you would stem to database, and you would find something. You can look up Microsoft, et cetera. Right? So this is totally straightforward. How do you handle Boolean logic? Well, it's also pretty straightforward. So OR is easy. Term 1 or term 2, if you type that query, that's just the union of two postings lists. You look up term 1, you get a sorted ordered list. You look up term 2, you get another sorted ordered list. Those are the doc IDs that match term 1 or term 2. It's the union of those two lists. Term 1 and term 2, it's the intersection of those two postings lists, right? You look up Berkeley, you look up Windows, and then they're already sorted by document ID in the postings list. So you can just merge those postings lists looking for matches, right? So that's really fast because they're already sorted by doc ID. So it's really these two B-tree lookups. And even if those posting lists are very long, imagine they're extremely long, like you look up Justin Bieber or something, right? So you look up Justin and you look up Bieber, and you're looking for something that has both, right? So two really, really long files, but they're already sorted. So you just scan them both and merge them. So that's fast. Term 1 and not term 2 is set subtraction. I want documents that say Justin and do not say Bieber. All right, I'm looking for people who are named Justin and don't want to see the Justin Bieber stuff. Again, you take those two things, they're sorted by doc ID already, and that merge will do set subtraction. Find things here, see if there's a match here. If there is a match, don't output it this time. And if there's no match, do output it. So it's almost exactly the same as intersection. It's just inverse logic as to what you send to the output. All right, and then term or not term 2 is a little weird. So this is term 1, unioned with all the things that do not contain term 2. So all the documents on the web that don't say Hellerstein. That's a lot of documents, sadly, right? I'm just not quite that popular. So most times systems won't let you type that. And in fact, if somebody's sitting at Google right now, it might be fun to see if Google or Bing will let you ask a query that has an or not. I don't know what it'll do. Anybody online? No? Nobody's online? It's a little hard to believe. All right, well, we'll come back and ask you after the break what happened when you try to do the or not query at Google. It just ignores the or not?
I did a little or not by, and it just parsed the whole thing as text.
It just treated the or and the not as text? Yeah. If you do and, does it do the right thing? I think you might have to figure out what their Boolean search syntax is. All right, so Vikram's got homework while we're talking. Okay, good. He's on the job. He's a hardworking guy. So you can think about how to do this in SQL if you're sort of a weird relational dude, which I guess I am. I don't know. But, it's pretty straightforward. If you're going to do Berkeley database research, what are you doing? You're doing a three-way merge join of postings lists from the term index, right? You do the red thing is the lookup on Berkeley in the term index. The green thing is the lookup on database in the term index. And the blue thing is the lookup on research in the term index. You're joining them together on doc ID. That's the intersection, right? And this is all going to be merge joins because they're coming out ordered out of these term indexes. And you're kind of done. Oh, by the way, ordered by magical ranking function, okay, which we'll learn about in a little bit. I wrote this as joins instead of intersections. Why is that okay? Just in general, joins are not the same as intersections. Well, each doc ID will appear in each postings list at most once. All right, we're not going to put a doc ID in a postings list twice. So the word Berkeley occurs in my homepage more than once. My homepage will still only appear once in the postings list for Berkeley, as of now, as of what we've seen. Okay, so there's no duplicates in these leaf nodes that we're merging, and then when we merge them, whether you join them or intersection is the same because the cardinalities are 1. There's always only one of each doc ID in each join, so there's only one pair that comes in the output when you join it. So join and intersection both produce one output for matches and 0 output for non-matches.
And not works or not just the results, just like.
I see. Okay, good. I will bring that up in a sec. Let's finish this one. So joins are equivalent to intersection, and the query plan, as I said, is an index scan on those 3 indexes and a merge join, ordered by doc ID. So Vikram says that Google's response to A or not B is just to say nothing. There's no answer. All right, which is obviously wrong because it should be bigger than A. Interesting. Okay. The reason I'm showing you this in SQL is because we're actually going to enrich this whole thing in a minute. And I find this whole business of all the tricks they throw in the bag with information retrieval, it's just going to be patterned over this query. We're just going to layer things onto. It's not so much the SQL as the query plan that's going to be useful for us to keep our eyes on. But we're going to be changing the schema as we go and expanding it. So if you prefer to write this with intersects and excepts, you can. So here's Windows and Glass or Door and not Microsoft. Right, this is the one we started with. The blue stuff is the Windows lookup. The and is the intersect. The green stuff is the Glass or Door. All right, and the and not is the except, and the Microsoft is the red stuff. So it's still just a bunch. All of these things can be done with merges of those postings lists. So the whole query plan, even when it gets messier than this, is just one big merge of a whole bunch of index lookup results. That's why it can be pretty darn fast, right? And really, when you think about this query that they're supporting, it's just that query plan. You're always doing B-tree lookups and scans, B-tree lookups and scans with merges. And that's why I say it's sort of customized. That's the query engine you build, is a query engine that can only run that plan. You won't implement hash joins. You won't have an optimizer that tries to figure out different strategies. All your accesses will be down through these indexes to these postings lists. So you'll compress the postings lists in a special postings list format because you know they're always going to be of a particular length, right? You'll custom tune this whole thing to this merge join query over index results. So the interesting bit is magic rank. That's the secret sauce, and we'll get to that in a bit. But I want to get through the nuts and bolts a little bit further. Any questions up to now? All right, we've sort of rolled our way through the 60s. We're getting to the early 70s soon. Not yet. Everybody good? All right. Here's something a little fancier. Suppose you want a phrase like happy days. All right. Well, the way we're going to get a phrase is we're going to augment the schema we had before with a little more information. So as we wrangle our files, in addition to storing term, comma, docID pairs, we'll store a position, which is going to be the token offset. Think of that as the word offset if you split it up by spaces or by white space. It's the position of that word in the document. Now, if Hellerstein, well, let's say, now if Berkeley appears on my web page 3 times, we'll store it 3 times, once for each of its positions. It's the 3rd word, it's the 12th word, and it's the 56th word on my web page, okay? We'll still do an index on term, so we're still going to look things up by Berkeley, let's say, but the postings list is going to be sorted by docID, comma, position. Okay? So the postings lists are still sorted by docID, but if there's many things on a docID, they're sorted by the position. The position numbers are there. All right? And then what we're going to do is we're going to run the Boolean query we ran before for happy and days. So we'll get the happy postings list, the days posting list. We'll start merging. If we get a document that has both happy and days, now we're going to look at, the docID 27 is here, docID 27 is here. Now let's look at merging on postings, on positions, sorry. And if the position of this guy is 1 before the position of this guy in the document, this was word 5 and this was word 6, then you get the phrase happy days starting at position 5. Make sense? So as you merge, you're just looking for things that are adjacent. And you can relax it. It doesn't have to be 1 off. It could be plus or minus 2 or something like that. And that might account for a couple of adjectives thrown in between. Happy freaking days, right? That'll be fine. So that's all. It's still that same query plan. Right? You're just doing a little bit more careful predicate on what you output. Okay? And so you can do near instead of 1. Got it? So it's pretty simple. When you start to do near, you might have to rewind your merge a little bit. If you say, within 1,000 of, you can imagine you get this one, and this wasn't within 1,000, but, you might have to be a little careful to rewind this one when you look at the next one. It's a minor detail. So far we have done Boolean search. We've done Boolean search on phrases. Okay. One other trick that's probably not in the slides, but that's pretty useful, is sometimes you want to take a word like database. This might be, if this is in the slides later, I apologize. I looked at them last night. I don't think it is. And you might want to split it up into substrings of a particular length. All right? So let's say we do length 3. That's pretty typical. These are often called trigrams. And what that means is we're going to store dat, and we're going to store atta, and we're going to store tab, and we're going to store abba, and bas, and is. And for all of these triplets, all these trigrams, we're going to associate them with this document. Okay? So now I got a document that's not a bag of words, it's a bag of trigrams. Why would I do that? Anybody know what trigrams are good for? A bunch of different things, but there's a basic one. Yeah? So you can do pattern search, right? So if you wanted to do, star, data star, That is dat and ADA, right? With position off by 1, right? So you can do some wildcard searches. You can't do regular expressions in general, but you can do some wildcard searches. What else? Yeah. Genome sequencing, nice. A lot of approximate string matching in general. So it's a little easier for most people to relate to just misspellings, right? So if you have an index like that and somebody says, data bake. Well, if you break this up into trigrams and you search for dat and ADA and tab, you will find a pretty good match on database. It won't match on all of your terms, so you don't want to do it and. But you might want to say, look up each one of these, merge them, and keep things in the output if they match on a lot of the terms, right? Which you can imagine extending things. So even actually if you don't do indexing, this is useful in memory to do string comparisons. You can say how many trigrams overlap between the query string and the stored string. Right? But the nice thing with an index is you can look these up very quickly on a big corpus. So instead of saying, you can only imagine how would you do this if you didn't have trigrams? You'd have to scan through all the words. How else would you figure out where does data show up? You'd have to delimit the document into pieces where you can look at smaller pieces. Those pieces are these trigrams. Right? And then you can look in the index just for 2 things instead of scanning through the whole corpus. Okay? So you can play the same games that we did for phrases, you can play with n-grams. All right? And by the way, 3 seems to work pretty well. You start to do 4 and 5 and 6, and it doesn't pay off very much. If you do 3 and 4 and 5, you get most of the juice out of 3. It's just sort of the statistics of how letters get used. Now, in genomics, that might be different. Right? So you have to look at your domain. Right, but it's good for approximate string matching. Okay? Cool. All right. It's all well and good to be able to look things up and say, here are all the doc IDs that match my document, but that's not what's displayed by Google. What's displayed by Google is actually the content, right? So the inverted file is going to have string position doc ID. You don't want to actually store like a URL there. You want to store some encoded doc ID that's nice and small and compact. URLs are big textual things. You want to compress that down to IDs. It's kind of normalization. And then somewhere else you have a table that maps ints, those doc IDs, to URLs, right? So we just normalized out, instead of storing URLs in the inverted file, we store doc IDs in the inverted file, URLs in the files. And maybe for each file we also store a text snippet that describes the file. Or maybe we store the full content of the file if it's not that big, right? All right. And so to do this, we're just going to need to do joins at the end of your query once you get all those doc IDs out with the files table. Right? So we'll build a B tree on term to get the lookups in the inverted file table, and a B tree on files.docid to do the lookups after you get the IDs out of the query to do the lookups in the files table. So that's that final join step between the queries we saw in the previous slides and files.docid. Right? So we're going to take a query tree like that one and add one more join on the top to look up the documents. All right? Now, I'll point out that last join on the top is an index lookup join. It's not a merge join. It's actually a nested loops with an index. It's an index nested loops join at the top. All right, so that was merge join, and then the one to look up the docs is index nested loops. One of the things you've noticed when you've used search engines is they don't return all the results. They return the first K for some K. And so they lazily look things up. And this is like that thing we talk about when we talk about streaming query plans. Right? This query plan streams. So here's, term 1. Here's this merge join with term 2. Here's the merge join with term 3. Merge join with term 3 index. And now what we're going to do is we're going to do a index nested loops join into documents, or files, into files. As you start merging these guys, you're scanning T1, T2, and T3 via getNext, if you like. Okay, right? And answers are starting to come out. You look up those answers immediately. A tuple comes out here with matches on all those terms. You look up the file and send it to the output. Another one, you send it to the output, etc. But that web form is pulling the first 10 results to show the first 10 on your page in a kind of streaming fashion, right? It pulls up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You've only done 10 lookups in this index, and it stops. There's nowhere in the middle where we materialize the entire result of the join. That would be terrible, right? If you have 1 million search hits, you don't want to actually store anything of size 1 million in the middle here. So there's no hash joins, there's no sort merge joins, there's none of that weird MapReduce thing where you store the intermediate result to the disk. This whole thing is iterators and streaming, okay? Because you only want to do this lazily. You just want one results page at a time. All of this stuff is textbook query processing. You know how to do all of this. Right? All we've done is define some schemas and some indexes. All right, what about updates? I mean, after all, periodically you add something to the internet and Google finds out about it, right? Well, one thing they do is they crawl the web to go find those things, and we'll talk about that in a minute. But when they find something new, what do? Well, these engines are designed to be query mostly. They're supposed to be super fast at query time, which means you don't want to be spending a lot of time doing insertions in them, right? Unlike a traditional database. So insertions and deletions and modifications are very rare in the workload, and they're not very important because nobody cares if you get that update in there now or an hour from now. It's not that big a deal relative to serving the queries. All right, so we're going to trade off insertion and modification time for search time. So we're postponing updates. And typically the way that these things are implemented is there's actually not one index on a given machine. By the way, all this is parallelized like crazy, right? But it's parallelized in exactly the way we always learned. It's hash partitioned, and it's just run on a bunch of nodes. Okay, so the parallelism actually is straightforward also. We can go over that if you like. It might be in the slides, it might not. But it's all this stuff just parallelizes in a straightforward fashion. So think about on a single machine still. What we're going to keep it on that machine is not just one index for the corpus dot term, right, which is the basic index. We're going to keep that's yesterday's index. Here's an index of new stuff added in the last hour. All right, here's an index of stuff that was added 2 hours ago, 3 hours ago, etc. So when inserts come in, we're just going to put them into a new tree. All right? We're not going to worry about updating this guy. We're just going to insert stuff into the new guy. And if you really, really want to delete stuff and you want to support that, which, by the way, most of these systems don't bother with this, but if you want to, you can keep a separate index for deletions. These are things I want to delete. And you put them in an index. These are term, doc ID pairs that I don't like. And then at query time, what do? Well, you take the union of all this stuff. So you do a lookup in here, and 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 you form the union of those. And then you do an except, if you need to, on this index to mask out the things that people wanted to delete. So we're actually just accumulating history here. We're just accumulating inserts and delete requests in their own separate indexes. We're not updating this index. And then, oh, by the way, once in a blue moon, you might take this machine offline for a minute and merge these together. You say, okay, you know what? Let's, in batch, take this thing offline, not worry about concurrent access, and merge all this stuff in. Merge in the additions and delete the deletions. Or, which is more typical, you will rebuild this whole index from scratch on another machine. So this is machine number 1. And you say, you know what? Machine number 1 is getting kind of full of these little pieces of index. Let's allocate one of the free machines in the cluster we have, machine number 2. Scan this and construct a new clean index, wipe machine number 1, and throw it back in the pool. It's just not worth the IOs to go messing around fixing up these indexes. It's much better to just bulk load a new one. Okay? And there's a simpler version of this, which is you just turn this machine off, and you go copy this from another replica. Right? Because these things are going to be replicas of each other's little partitions or shards of the database. Right, so we're going to avoid anything with like interactive updates to these indexes. All right, this is sometimes called a log-structured merge index. It's a log in the sense that you log all the insertions in a new index and you log the deletions, you don't apply them, and it's merged together. So at least one person calls this log-structured merge indexes, and it kind of caught on, but it's been going on in information retrieval forever. Right, and you typically build a second index on a separate machine at scale. So there's no concurrency control problem other than like no one can access this machine anymore. And Oh, yeah, because you're not doing deletions or anything like that, your postings lists can be compressed. So imagine that in the postings list, which I showed you before, you have Berkeley. What are all the documents that contain the word Berkeley? Well, 3, 4, 5, 7, 17, 141, 142, 143, and 144. One compressed representation for this could be 3 through 5, or even 3 through 7, except for 6, 17, 141 through 144. That's a range compression, right, or run length encoding of this list. With deletions, it's kind of annoying to uncompress this and recompress it. But we're not going to do deletions, right? Which allows us to be really aggressive about the compression. Not only can you do run length encoding, you can do Huffman codes, you can do whatever you want, because this is a static set of data. This actual postings list will not change. Any changes that happen will happen in a separate place on a separate index. So you can compress the crap out of the bottom of these things, right, which is going to make your I.O.s really fast. It's going to give you more CPU work, but it's going to make your I.O.s really fast. So all that stuff of avoiding updates in the index makes read time very I.O. friendly. But it's things you wouldn't do in a relational database with interactive updates, potentially, because otherwise your transactions all are going through all these crazy indexes, and it's not worth the trouble. You do it in a traditional relational database, you would do it on a single index. Okay, so hopefully you can see at this point some of the places where database, transactional relational databases and information retrieval systems diverge, right? Text search engines are going to tune their essentially one query engine to their one query that they have to run to death. And that's awesome. If you have a system like that where there's really only one thing it needs to do, you can really make it go really fast, and it's really fun. It's fun to engineer for that. It's also fun to engineer for generality. There's different kinds of fun. I guess the other thing I would just highlight, though, is that the building blocks of this are all the basic building blocks. You know how to do indexing. You know how to do joins. You know how to do data flow pipelines. You know how to parallelize algorithms like joins, right? So you basically have all the information you need to build a kind of pokey Google with bad ranking, right, which isn't actually that bad. So if you look at a package like Lucene, which is the open source indexing package that is in the Apache stack, it comes with Hadoop and all that, it's not that far off what you just learned. All right. I'm going to teach you the basic ranking scheme, which is called TF-IDF, and then you'll have everything you need to build Lucene, essentially. So, the stuff we learned in this class, bottom line, one of the reasons the information retrieval lecture is short is because all that stuff we learned building up to what's a relational database is the same stuff you would learn building up to what's in an information retrieval system. That said, because it's a special case scenario, there are a ton more tricks. So ranking is the key one, and I'm going to talk about that next. There's been kind of back and forth fads as to whether to make visualization of search results interesting. Like, let's look at a graph of the search results clustered together with related documents. None of that's really caught on. It seems like, at least with web search, the best thing you can do is just give people a really well-ranked list. But under the covers, there's stuff like document clustering. So I'll give you an example. The ranking function that most search engines use is not only based on relevance. Right? Not only do you want the top most likely matches, but you want some diversity in that list. So if you search in, actually somebody should do this if you have your web search engine open, Google for Jaguar, or Bing for Jaguar if you like. And I suspect you will get at least one hit that has to do with the car, at least one hit that has to do with the cat, and maybe one hit that has to do with the football team. Shout out if you get results for the car when you type Jaguar. Raise your hand if you get something for cats. And raise your hand if you get something for football team. We're in Berkeley, and they have geo, so maybe not. I bet you if you lived in Florida, you'd get the football team. So point being, they actually do cluster the documents under the covers into what they believe are related topics, right? And then they pick from those clusters in a biased way to make sure they cover a bunch of the clusters. They pick from each of them. So there's clustering going on under the covers of what documents seem to be semantically related. So that's an example. There's other examples of ways you juice that stuff. Under the covers, more on the performance side, there's a million ways to do compression for better I/O performance, to make those postings lists smaller, to make things fit into RAM and into processor caches. Okay, If you've programmed with any of the open source from Google, you'll know that they've got their network buffer layouts, protobufs, the same as their disk buffer layouts, the same as what they work on in memory whenever possible, so they're never copying data. It's always in the same binary format and the same units of transfer. Stuff like that starts to matter when you're really trying to tune this. Yeah?
Tools like grep work like this as well. I can't really believe that grep would work index on the file,
Good. So the question was, for those of you who couldn't hear it, does grep work this way, the Unix utility? And the answer is no. Grep is a sequential scan. All right, so grep takes a regular expression, which is actually more powerful than what you'd get out of, say, trigrams. Okay, and it scans through your all your files. If you grep, if you say find / whatever pipe into grep, it will look through every byte on every file on your disk interactively, which is kind of a drag. But it does build a very interesting, I think grep has a nice automaton that it builds for your regexes. I think it optimizes it in interesting ways. There's interesting stuff under the covers, but it doesn't limit the amount of I/O you do. Yeah. Prior to the internet, there were projects to do interesting text indexing for your Unix file system to give you very fast grep, essentially. And some of the people who worked on those algorithms actually impacted the genomics research literature, so string matching for human genome alignment. And some of them went off into internet companies like Yahoo in the early days, and I think some of them did both, actually. So there was a group at Arizona that was doing a lot of this kind of let's make grep go fast, and they were proto-web and genomics, computational genomics. So it's kind of cool. All right. What else did I leave out on this list? Oh, yeah, all the linguistic stuff. So synonyms. How do you know about synonyms? How do you deal with misspellings? We did a little bit of that. How do you deal with abbreviations? If you search for IBM, it will find documents that say International Business Machines at Google because they kind of got that juiced. There's all sorts of interesting questions about how you do that. One thing that I do have slides later on, they're kind of high level, but we might go through, is how do you write a good web crawler? All right, it's easy to write a bad web crawler, one that's either too slow or too fast. We'll talk about what that means. It's hard to write a good web crawler. That took a while. Dealing with search engine optimization, or really web spam, right? So if there's a third party that wants to get high in the rankings and will do anything to do that, how do you make sure that they don't get control over the rankings? The rankings are somehow fair, right? And then things like customization. Like, it is quite possible that the reason we didn't see Jacksonville Jaguars is because they knew our geo was in California based on our IP addresses, okay? But more generally, they know your search history, and they customize searches to your search history. So how does that work? So all these soft things about ranking, there's some linguistics in there, there's some statistics in there, there's some graph theory in there. There's just it's a soup. It's just a whole bunch of different features. Okay? So to sum up, today, the first half of this lecture, you already know the basics. Inverted files, which is just a shredding of the document into a relational table with an index. That's the workhorse of all text search engines. And all they do is intersect union and set difference by postings list merge. Look up in the index, merge what you find at the leaves. Most of the other stuff is really neat, but is pretty custom for web search. All right, so things as I just talked about. For the record, I taught all this for this class, kind of using terminology that we're familiar with. But if you if you tell your cool Google friends that you learned about web search and it's like this SQL query with these 17 lines, they will laugh at you, as they should. Okay, but more generally, there's a different set of terminology that gets used from the information retrieval literature. By now, the great thing about the web being such a big deal is that everybody in computer science kind of got together around it. So you had theoreticians and AI people and database people and information retrieval people and operating systems people and networking people and just everybody, right? And so we finally kind of shared words. And this isn't as bad as it used to be, but there was a time when I taught this class where information retrieval and database people couldn't talk to each other. So anyway, here's some terminology from IR lingo you should know. The corpus is the collection of documents, like I'm indexing the web or I'm indexing my file system. A term is this thing that you index. It's the searchable thing, okay? An index is not like a data structure like we talked about. It's a mechanism to map terms to documents. So it's this whole kind of shred the document, build a schema, build an index over that schema. An inverted file with the postings list is what we saw it was. All right, and you should know all that stuff. All right, so those terms are important to know if you talk to search people. All right. I think we will skip this. Let's take a stretch, and then we'll talk a little bit about ranking. All right. So let's jump back in. Any questions before we go on unranked Boolean search? Pretty simple stuff. There's barely an algorithm in sight, right? This was pretty much, we didn't learn a new algorithm yet today. So the interesting stuff kind of comes now in some sense, once you already know databases. Indexes on the different keys?
Or on the, I guess, like, does those triangles represent, like, one index on one, like, set of, like, what is one of the big triangles represent?
Sorry. Yeah, let's go over this again. So this is, let's be really specific about what's going on so I don't lose any of you. So ignore this for the time being. This rectangle is a computer, machine number 1. Okay? And what we're describing here is what's sometimes called a LSM tree. Log structured merge tree. This collection of triangles is going to represent for us what we would traditionally represent in a single B tree index. But instead, we're going to implement it with a set of B tree indexes. And here's how it's going to work. Let me start over. On the happy day when this machine is first loaded, we bulk load a B tree with all the good stuff that this machine is responsible for indexing. Okay? And it's, some subset of the terms from the corpus. Or maybe it's some subset of the documents from the corpus. But it's some subset of the data, and it's being indexed by terms. Okay? It's a B tree on term. Now what's going to happen is over time, we're going to want to add things to this B tree. Maybe every hour or every 5 minutes, we're going to bulk load some more stuff. We crawled the web. We found some new docs. We're going to load them in. Rather than have B tree splits happen and manipulate this data structure, we're just going to build another index on the new data with new postings lists. Maybe some of the same terms. So database might be here as a term. And if you create a new document on the web and it gets crawled and it contains the word database, we won't add you to this postings list. We'll insert you into this index with a postings list for you and all the other pages that had database on the most recent batch load. So we batch load in a new index, which may have common terms with this index. And if something disappeared from the crawl since last time, some document was deleted, we will not delete the postings for it here. We will create this red index. Maybe it also has some documents that had database in them, but those documents are gone. So their doc IDs will be stored here. Okay? And then when a query comes into machine 1 looking for database, it's going to form the union of the answers from all the green indexes to the query database. And then it's going to subtract out anything it finds in the red indexes for the word database. And that's the answer it gives from this machine. So we don't do deletions and insertions here. We do insertions by batches of new little triangle, green triangles. Every time you do a batch insert, you get a new index like this. And every time you do a batch insert with deletions, you get a deletion index like that. Make sense? You could just insert and delete from here. But the problem is you're going to do a lot of random IOs walking up and down this thing. You're going to do a lot of page splits and all that kind of stuff we learned in our B-tree algorithm. Remember, the bulk load algorithm for the B-tree was mostly sequential IO, and it was really fast. So if you're doing this in batch anyway, it's way faster to build this thing than it is to take the contents of this thing and insert them into here. It's the same argument we made when we talked about bulk loading and B-tree. Bulk loading is faster than batch insertion. Yeah, you sort before you bulk load. Yeah, that's part of the bulk loading algorithm, actually, you sort the input. Again, half of that I/O is sequential. Right? And if it fits in memory, then it fits in memory. Okay? Yeah?
What's the fan-out comparison between those three?
The fan-outs should be about the same. It's just the height's lower. Okay. These are just less data. It's the same code generating the same data structure. It's just this is last week, and this is the last hour. You would merge periodically, and you might. This is the kind of thing where like you have to operate a search engine for a while to tune it up. But I'm sure Lucene has a flag for this. But you'd tune this so periodically you would either merge these. Like let's do this. Let's stop pretending we're Google for a second. Suppose you want to index your laptop, all right? And you turn on Lucene, or you spotlight search on your Mac or whatever. It's going to have one of these. And periodically, a little daemon process wakes up and builds one of these. And then periodically, less periodically, a daemon process wakes up and merges these into here, right? Just to kind of clean up this mess of unioning all this stuff together. Okay? And how often does that happen? Well, one good heuristic is if this stuff adds up to the size, if the union of all these things is as big as this thing, then it might be time to merge them, all right? And that you can get, then you can give bounds on how long this chain will be. It'll never be more than linear in the size of this thing. And you can do that recursively, too, if you want. So you can have little mini additions, and then you can merge the mini additions into the bigger one. So you can kind of take these things and make a big one out of them periodically and then recurse. So there's games you can play, but we don't have to get too fancy. Having said that, for your laptop, if we go to Google now, it's not worth doing any of this. You just blow this machine away and you rebuild the contents of this machine from scratch. Right. So the union of rebuild is an entire computer, not a data structure. Right. But the basic idea is just it's a union of positive stuff and negative stuff, and you just append to that union and then periodically consolidate. Everybody got this now? Does this make sense? This design pattern is becoming increasingly important, actually, for high-performance main memory databases. So this notion of, like, you build a log of activity, both positive activity and negative activity, and you don't make structural modifications. You just accumulate stuff in a log, and then as needed, you kind of put together the log to give you the answer. That can actually give you good performance for in-memory data structures because you don't end up setting locks in here to modify this thing in memory. And we won't talk about that in great detail in class, but you should know this pattern, this log and merge pattern. It's pretty broadly useful, and I think will be an increasingly important design pattern for high-performance systems down a level in the memory hierarchy now, down on the how do you make things work fast on chip. I won't say anything more about that. Are we good? What other questions on Boolean search, if any? Okay. Well, let's spend the last 20 minutes before break on ranking. So if you go back to Cornell in the early 70s, they talk about ranking this way, a vector space model. So imagine every word that you could ever want to index. This is before the web, mind you. The web has a lot more words than the English language, okay? But back in 1970, let's worry about all the great works of mankind, all the documents in a library. It's a phenomenal amount of data. Yes? Well, imagine this. For every word that appears in any book ever written by mankind, it is a dimension in a high-dimensional space. Whoa. Okay, how many words are there? I don't know. There's like 200,000 words. I don't know, there's a lot of words, right? So think about, there's like 1 dimension, 2 dimensions, 3 dimensions. You get pretty confused with 4 dimensions. Every one of these dimensions is a word. Okay? This is some crazy stuff in 1972, right? I mean, it's not if you're a mathematician, right? If you're a mathematician, you're like, oh yeah, a vector of 10,000 elements, it looks like this. Index 1, index 2, index 3, index 10,000. That's fine. I'm good, right? You try to think about it geometrically, it's really kind of mind-boggling. Okay, but we have this vector space model. Every document is a vector. We do this all the time now in machine learning, by the way. It's like no big deal. But imagine there's 10,000 possible terms, and every document is an array or a vector of 10,000 counts. How many times did each term occur? The first slot is for the word a. The second slot is for the word which is a kind of lava, I think. And it goes on. The next word is Alabama or whatever, right? And you just have a count. There's 2 A's and there's 1 and there's 17 Alabamas in this document. You just build a big vector, right? All right, and so every document's represented by a vector. And if you think about it, that vector is a vector, right? It's a point in 10,000 space. It's not a point, it's a whatever. It is a point in 10,000 space, yeah? It's a vector. So that's cool. What's similarity of 2 documents? Similarity of 2 documents in vector space, like you care, but maybe you care, is their distance in 10,000 dimensions. Maybe their Euclidean distance, let's say for now, okay? So how far apart are 2 points in document space? That's how close those documents are to each other. So a query, what's a query then? A query is just a document also. Whoa, that's cool, right? You type in your 2-word query, it's like you've composed a new book in the library. And I want to know how close your book is to all the other books, because the close books to your query are the books you like, right? So we're going to rank all documents by their distance to the query document. That's ranking. It's the vector space model. So, your query, you put a point in space, and then you fly around in 10,000 dimensional space till you run into some stuff, right? And that's how you do querying, which is all well and good, but how do you implement that and make it go fast? Well, before we even ask that, what really is the right distance metric? Is Euclidean distance the right metric? It seems like it's not, or maybe not without some normalization. So let's think about this for a sec. 2 long documents, like 2 pieces of work by Shakespeare, are going to be like really far out from the origin because they will have lots of ye's and thy's and all that kind of stuff, right? They'll have lots of repetitions of words, which means they're going to be far, far away from the origin. Your query, which is like, find me like Romeo, Juliet, right? It's going to be right near the origin because there's only 1 occurrence of each of the terms. So 2 plays by Shakespeare are probably closer to each other than you are to any of them, and that could be kind of a problem. Long documents, forget about the query and the documents, but just the guy who writes the long document, like the really verbose stuff, it's going to be way, way far away, and short stuff is going to be close to the origin, and you'll always end up getting short documents back when you ask for queries. It seems like a bummer. If you're interested in prose and not poetry, you're going to be sad. Get a lot of poetry back. Okay, so the solution is we're going to normalize each dimension by the vector's Euclidean length. So you get one of these vectors, figure out how long it is from the origin, divide by that length, so that every dimension's contribution has been divided by the length of the document. And if you do that, what's going to happen is every document's now a point on the unit sphere, because we've normalized everything to the same length. So everything is the same distance away from the origin, okay, and it's just points on a sphere. That's kind of cool. All right, now, geometry. Now that everything's points on a sphere, it's like trigonometry. It's even easy geometry. The cosine of the angle between 2 normalized vectors on the sphere is their dot product. All right, this is called the law of cosines. And I had to remind myself about it, so I looked it up on Wikipedia like you do. Okay, and you are welcome to follow the link. And so for normalized vectors, once you get these things normalized, rather than compute their cosine ranking, you can compute, rather than compute their Euclidean distance, you can compute their cosine ranking. They're the same. Once you've normalized, that intuition we had that they should just be close to each other is the same as figuring out the cosine of the angle between them. Okay, which sort of makes sense. Okay, so now we can just figure out which one of these things is easier to implement, which is almost certainly the dot product of the 2 vectors, right? Dot products are easy to compute. So that's what we'll do for our distance function. So that helps, okay? So now we can compute the cosine of the angle as the dot product. That's the same thing as the geometric distance, but they're the same. Okay. But here's the last thing. So we've got cosine distance. That's all really good. The thing is that not all dimensions are actually the same. All right. There's some dimensions that we like better than others. And this leads us to this thing called TF-IDF. So counting occurrences of words, just raw, isn't good because of the words and because of the counting. So we want to favor words that are repeated in the document. If you say, squirrel, 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 lots and lots of times in your document, it's probably about squirrels, right? You probably care a lot about squirrels. So we want to favor the repeated terms. We also want to favor the unusual terms. So if you say, I don't know, what's a good unusual term? I won't do something funny because I always get in trouble. Let's suppose your unusual term is this because it's the serial number of the network chip on your laptop, right? Right? That doesn't occur in a lot of Shakespeare, but it definitely will occur in the product manual or the order form for your laptop's, whatever I just said, chip. Yeah? So that's an unusual term. So if you have a crazy unusual term, that should be important too. So the first of these things, favor repeated terms in the document, has to do with the document and how many times each term occurs in your document. The unusual thing has to do with all the documents. How often does that occur in all the documents, right? That's what makes it rare or unusual, is that it doesn't occur very often in other documents. So the first issue is about your document. The second issue is about all the other documents, or including yours, okay? Maybe in some government database, this is a really common term. I don't know. Okay. So what we're going to do for this weighting is we're going to compute TF, which is the frequency of the term in your document, times IDF, which is 1 over the frequency of the term in other documents. So to get this exactly right, the rank is going to be the number of occurrences of T, that's TF, times, and we're going to take a logarithm here to keep this kind of not growing too fast, the total number of docs divided by the number of docs with this term. So it's 1 over the fraction of docs that contain this term. Okay? So we're going to like things if they have high term frequency, and we are going to like them if they have high inverse document frequency, which is to say they have low document frequency. They're rare terms. Okay? TF is the first of those things repeated. IDF is unusualness. Right? So then all we're going to do is we're going to take our, instead of using the raw counts we were doing before, which is just TF, we're going to weight all our occurrences in this vector with log IDF. So take this vector like we had before, and instead of storing these counts, multiply them by the log of the IDF of the term that they belong to. Okay? And then this is the vector for the document. And then do your thing where you normalize it, put it on the sphere, and compute the cosine similarity. Right? And that's pretty much was state-of-the-art till the web was invented. All right? Notice that the log damps out the IDF. Just to convince yourself that's right, what's the IDF of a term that occurs in all documents? Log of total number of docs divided by total number of docs is 1. What's the log of 1? 0. All right? What's the log of a document that occurs in almost no documents? Total number of docs divided by 1 is big. Right? So that's what we want. Yeah? Good. So the word the will kind of come out in the wash anyway as 0. So we might as well just not index it. That's what we're saying. Okay. So you can do indexing for TF-IDF to make this go better. So you don't have to compute the comparison of yourself with all documents on the web. Your query shouldn't be compared against all documents. We're going to add a little bit more information to our schema. Okay? We're going to have a table called term info that for each term is going to say the number of documents that term occurs in. All right? This is a view over the corpus, right? This is just a query we could say. We could say it's an aggregation query. It's a count query over the corpus grouped by term, right? But we're going to store the results. It's called a materialized view. All right, so we're going to keep this thing, the term info. This is the denominator of the IDF, right? You should be able to write down the SQL for this thing. It's easy. All right, and so the inverted file that we're going to store is going to have the term, the doc ID, and then we're going to compute that rank and store it here, which is the TF-IDF. We'll store it right here. This term, what's its doc term rank? That's going to be stored with the document, or with the term occurrence, which is actually denormalized, all right? This is expensive. But we're not going to update this very frequently, so it's okay. Right? We're not going to update the term info table very often. And even if we do and things aren't exactly accurate, who's to know? Right? Maybe our ranking won't be 100% perfect. So, we could do this in SQL again. There's our Boolean result. That's just what we had before, Berkeley database research. All right, and remember we had magic rank function, right? Well, here's what we're going to do. We're going to take the Berkeley query term rank and multiply it by the TF-IDF. Yes, sorry. The things that are on the right-hand side are from the view Boolean result. The things that are in the box are constants across the whole database. All right? This is, no. The things that are in the box are your query. So if you write a query, this is your query document. If you write a query that says Berkeley database, Berkeley research, all right, well, the TF of Berkeley in this thing is 2, and the IDF of Berkeley is something from that table up at the top, and that's what we store right there. Berkeley query term rank is TF, IDF for the term Berkeley from the query. And what this expression in the select list is doing is just the dot product of your query here and the documents in the database, right? That's computing that cosine similarity, is that dot product. It's the sum of the products of the terms. Okay, so this Berkeley query term rank's coming from the query. It's 1, 2, 3 times IDF of Berkeley in the corpus. And then it's 1 for database times IDF of database in the corpus, and 1 for research times IDF of research in the corpus. Make sense? We still haven't said how to order it, but we could order it just by this dot product, and that would give us cosine similarity. That would give us TF-IDF ranking. Everybody good? That's the SQL. Now the query plan for this, we're going to have to give some thought. All right? Because now we're not just merging our postings lists and sending them to the output. We have to rank the output. So let's see what this looks like. In the postings list, we can have these DT ranks, okay? So, or we can get them on the fly as we do the merge. So we're going to get our Berkeley, our database, and our research. They're sorted by doc ID. They've got the DT ranks, the TF-IDF for that term in that document. All right? And what we're going to do, first of all, is we're not going to rank anything else but the things that match on either Berkeley or database or research. In fact, they're going to have to match on all 3 of those things for them to be in the output. This is just a heuristic. Why is this just a heuristic? This query plan right here is not actually computing the true TF-IDF ranking. Why not? Can anybody think of a scenario where there's a better document than one that this query would give, this query plan would give? All right, well, notice the join of all 3 of the postings list. Here's a hint. So we're going to have Berkeley and database and research in the document for it to be in the output. Is it possible that there's a document out there that's a better match to your query that's missing one of those terms? Well, let me give you an example. Instead of searching for Berkeley database research, I search for Berkeley database 2007-4. Okay? Probably there's a good batch on this that maybe doesn't have a database or Berkeley. That's probably a better answer to this query than like my homepage. Right? In terms of TF-IDF proximity. This has got an extremely high IDF. This is a very rare term, which means it's going to be very close to any other document that contains this crazy term after we normalize. Right? After you convert these things with your TF-IDFs, the things on the unit sphere that are going to be close on this dimension are going to be the things that have this word. right? Things that don't have this word are going to be super far away because this is a rare word. So it would be a great match to find something with no Berkeley, no database, but this crazy term in it. And this query won't find it because it's insisting on joining all three of them. So what do we do about that? Well, this computes things that have the conjunction of all three. What might we want to add to the output of this query? How about documents that only have 2 out of the 3, right? Or documents that have only 1 out of the 3. So we can take this query, which is the conjunction of all 3, union the thing that has Berkeley and database, union the thing that has Berkeley and union the thing that has database and then throw all of them into the ranking function. We could do that, right? And we could even go down to the level of single terms. Okay? If you type a query with 100 terms in it into Google, it's not going to look up the onesie matches, all right? But it might drop 1 term from each version. Right? I don't know, some search engines, I think it's true of Google, they'll tell you in the results if it's missing one of your terms underneath the result hit, right? And that's how it does it. It doesn't just do the conjunctive Boolean query. It also does subset queries, and then it ranks the whole business. Right? So it's pretty straightforward how to do that. And we're going to merge join the postings list for each term. Well, that's the usual stuff. But, all right, now what we have to do is efficiently compute that ranking, hopefully in a streaming fashion, so that we can compute the output. Remember, think about how this works. That join is going to happen. The join is just a merge join. The data is getting pulled up into your web page. Top 10 can just be get. And now I suddenly told you have to sort it by rank. Well, we know how sorting works, right? You have to read everything before you can begin to sort it. That would be super bad news if that thing where it said 10 million hits found, before it gave you the top 10, it sorted them all. That would be a disaster. Okay, so it's not doing that. What is it doing? Well, for each document ID that matches the query, we're going to compute the cosine distance to the query. This collapses the view in the previous slide. Right, so we're going to take these 2 things and treat them as one query. All right, and then what is it saying? For all the terms, right? Now what? Okay, now we got to think. And I forget how the next 2 slides go. One of them's better than the other. We're going to have to figure it out together, okay? All right. So what we haven't figured out yet is what are we going to do about this sort? All right. Suppose that the number of matches that come out of the join is still pretty big. All right. Now, sorting 1 million things isn't that bad, actually. It's not that big a thing. 1 million's not so big. But and hopefully, if you're Google, you just do this in memory, right? But still, like, this seems bad. How are we going to do this? Well, first issue is we'd like to parallelize. Okay? We want to take advantage of parallelism. So let's talk about parallelism, and then we'll come back to how do we do the sort efficiently. Okay? So if we're going to parallelize this business, and now that we're thinking about the ranking, we have to consider ranking in the parallelism. Oh, man, we only got 2 minutes left? All right, so I'm going to leave you with a big pregnant question over break. That's what we're going to do. We've gotten this far. Single node, TF-IDF, classical. It is now 1975 in Ithaca. We're good. Okay? But the challenge is how to make the sort go fast. Right? And the next challenge is going to be how do we take advantage of 1980s era parallelism? Okay. So when you know how to parallelize a join, right? You partition the data, right? And we're going to do merge joins. We want to do merge joins. So we're going to partition them in a way where you can merge locally, and then maybe do some more merging globally. Right? But we're going to want to do it hierarchically. So think about how you're going to parallelize this query plan, and then think about where should you put what data to make that parallelism work. So the key question is going to be how do you take this index and partition it across nodes? All right, and I'll give you 2 options to think about over break. One is you could partition it by term, right? So that this machine would be responsible for a particular set of words, and would get all the docs for those words. Another machine would be responsible for another set of words. Or you could partition it by doc ID. This could be responsible for a certain set of documents, and this could be responsible for a certain set of documents. And you can think about this query plan and think about which of those is better while you're at break. Have a lovely, restful vacation. I hope you can get your homework done before you go. That would be great. And if not, it's due Tuesday night after you get back.